This topic is nonlinear classifier, and we will see how we can make use of the optimal hyperplane classifier even in nonlinear space. So we have an input space, and the points in the input space are not linearly separate, like this. We do have a clear region of negative points whose labels are -1, and another region of positive points whose labels are +1s. Unfortunately, there is no straight line or a hyperplane in general which can divide the plus points from the minus points. So what if there is an unknown mapping where points are linearly separable? So this is the input space on the bottom left where the points are not linearly separable, and this is some unknown space where the points are now linearly separable. And therefore, we need to have some mapping phi from points xi, xj to phi xi, phi xj to the unknown space. And let this mapping be unknown because the space is unknown, so the mapping is unknown. And let's consider the inner product in the unknown space such that is there some other function k called the kernel function such that the kernel function in the known space is equal to the inner product in our unknown space. In which case we can operate on this kernel instead of going to the unknown space and computing the inner products of every pair of points in the unknown space. So this actually helps us to devise classifiers in the known space if we only know such a kernel kxi, xj, which is equal to the inner product in our unknown space. This will help us devise a linear classifier as long as we replace the inner product with the kernel in our input space. Here's an example. This is an input space. It's two-dimensional. So each point x has an x coordinate and a y coordinate. And let's consider an unknown mapping phi such that this x maps to x squared, square root of xy, y squared. It's a three-dimensional space, but it's not known to us. Now consider 2 points, xi and xj. When we map it to the unknown space, phi of xi is xi squared root 2 xi yi squared, and phi of xj is xj squared square root of 2 xj yj and yj squared. But it's unknown to us. What we need is the kernel. So this is our unknown space, and the 2 points which have been projected from our known space, and the kernel, the inner product between them is this phi xi, phi xj, which is phi xi transposed times phi xj. And if we simplify it further, it gives us this expression, which is simply equal to xi transpose xj. So this is easy to compute. And we let our kernel function kxi xj be simply equal to xi transpose xj. And going back to the original space, if we simply devise our kernel, if we use our kernel kxi xj being equal to this xi transpose xj squared, then we are in fact finding out the inner product in our unknown space. We don't really need any other information from our unknown space. So that's what this nonlinear transformation is all about. So as long as our kernel is given by this expression kxi xj, xi and xj are points that are known in the input space, and this kernel function is devised by us to be equal to xi transpose xj squared, then we know that there is some unknown space where the points are linearly separable, and this kernel function is equal to the inner product in that unknown space. Mercer's theorem. Mercer's theorem gives us condition for the kernel function under which it is equal to the inner product in some inner product unknown space. So we don't have to know the transformation into that space. We can work with the kernel's function in the input space. And the condition, if we take finite numbers of samples xi and xj, then the kernel function becomes a matrix, and the matrix has to be symmetric, positive, definite. So this is the dual form of the maximum margin hyperplane formulation. So we maximize with respect to the dual variable lambda of this objective function, which contains a quadratic term, negative half lambda transpose h lambda and 1 transpose lambda, and subject to y transpose lambda equals 0, and lambda should lie in the range 0 to c. This is in case of soft margin hyperplane. Otherwise, the condition for a simple optimal hyperplane would be lambda is greater than or equal to 0. That's the only difference here between the soft margin hyperplane and the hard margin hyperplane. In the soft margin hyperplane, we have a constant c. In the hard margin hyperplane, c is simply equal to infinity. The only place where we need h later on is here and in this matrix, and here all we need is phi xi, phi xj if we do the transformation, and that's equal to this. So every entry hij, which is equal to yi yj times the inner product, can be replaced with yi yj times the kernel, and we don't need to worry about the mapping phi, which would remain hidden from us as long as the kernel satisfies some simple conditions. So this is the support vector formulation. The bias needs to be known, and again for the bias we only need information about the kernel, and we need to store the set of support vectors, and this is our final classifier. Again, in the final classifier we use only the support vectors, and we are computing the kernels with arguments x, which is our new input, and xs, which is x for a support vector. And all we need to do is compute the kernel between x, the unknown point, and the support vectors, and then we can get our label of the x, the unknown point x. This is what the linear SVM looks like, and this is what the linear SVM would look like if we were to operate in that unknown space. So we would be inputting phi of x, and then we would be computing the inner products before we do the summation and the bias to give us the estimated label of the input sample X. But we don't have to map anything to the unknown space. This is the nonlinear SVM, which works on the input space. All we have done is replace the inner products in the unknown space with the kernel function, and everything else remains structurally the same as the linear SVM working in the unknown space. And all we have to do is now devise a good kernel. Kernel is a measure of similarity between two samples, and for text data, you can devise kernels using keyword frequency. For string data, kernels are based on the smallest edit distance between two strings. For graphs, kernels can be defined, effective kernels can be devised using Laplacian eigenvalues, and we can devise kernels for emails using keywords, the senders, and the number of recipients, and so on. So in an actual application, one of the main tasks is to select a good kernel. That's the end of this lecture.